Today we are gonna study and see in real life something we have already studied last week. We will do it, we will see some non-idealities, sort of saying, of the operation amplifier with a non-inverting amplifier. We have already studied this circuit last week, and we have derived that if you have an input voltage applied here at the positive input of the operation amplifier without any resistance here, just straight to the positive input, this voltage is applied to the input resistance Ri, then there is a feedback resistance, and the output will be the ratio of the two resistances plus 1 times V input. And in this case we use two equal resistances, both they are 1 kilo ohm, so the output should be 1 kilo divided by 1 kilo is 1, plus 1, it's 2. So the output should be twice as big as the input, okay? And here we have the operation amplifier, it's an OP07. We have connected 1 kilo ohm here in the feedback, so this is the resistance which is connected between the negative input. This is the negative input. I'm not sure it can be seen on in the display, but okay, just trust me. This is the negative input, so between the negative and the output there is 1 kilo ohm, this resistance here, and another kilo ohm is connected between the negative and the ground. Then we have here a waveform generator. We generate 100 millivolt square wave with a frequency of 1 kilohertz, and we connect it between the ground and the positive input, so this is the positive input, and the output is connected to this scope, and we will see how it's gonna work. Now we can plug in the, we can turn in the channels. So the yellow channel is the input, which is connected in parallel through this BNC cable here, BNC connector with the coaxial cable to the scope. So we see that we have 100 millivolts because it's 1 millivolts per division. So here we see this waveform which is 100 millivolts. And if we turn on the power, you see that the output, again, it has the same scale. So you see that it's 200 millivolts because it's two divisions. Okay. And the system works. Okay. So you have an input which is a square wave. If you have a sine, you have a sine wave, okay? If you have a ramp, you have a ramp. Everything, well, it's just 2 times bigger. Whatever is the input that you have is 2 times bigger. Why I wanted to see the square wave? Because now you see something like that only because we are far away. But let's concentrate it here in this part at the beginning where actually something changes. If you're here, everything is hunky-dory, so it's like here, wait, you see, you are 100 millivolts, 200 millivolts, and that's fine. But what happens if we watch here? Okay, now you have, I have the different scale, so I'm not sure if maybe
no, it's very dark.
Yeah, so let's try to increase the intensity. No. Okay, we can do something like that. Stop.
Yes.
If you stop, you see it better. So now I have a different scale because the yellow, so the input is 50 milli and it's 100 milli. So they look the same, but just because the scale is different. You see that as the yellow, as the input changes from minus 100 to 100, it does not immediately reach the 200 millivolts. It takes some time. So here you see what we have explained last week. When you apply some change of some voltage to the operation amplifier, it will feel at the input that now there is a difference, and it has to, in fact, adapt and change the output, and it does gradually change the output until it arrives to the point where, again, the input, the difference of voltage between the two inputs, the positive and negative inputs, is again 0, and then it stops. In this case, we don't have a first order transient, we have a slightly ripple because you have a second order transient, but the principle is the same, okay? And this is something which is a limit of the operation amplifier. Here, ideally, it should go directly to the steady state value, so from minus 200 millivolts should go to 200 millivolts. But it's something that it cannot do so fast, okay? So it has a speed of change which is limited. Now, what we can do now is maybe change a little bit the frequency so we have more intensity, okay? But now we change the amplitude, okay? Let's see what happens if I change the amplitude, okay? You see what happens? Maybe I can change the scale and you will see it better. Okay, so this is with 400 millivolts. So let's go to 500. Okay, so we have some nice numbers. Okay. Okay, so again we go to twice the voltage. In the input we have 500 millivolts, and in the output we have twice as much, so one volt. Okay. Now, how long does it take to go from here to here? About a couple of divisions. Okay. Now, if I decrease the voltage, you see, now I'm back to 100, so I'm out of the trigger. Doesn't matter. So let's try 200 millivolts. Okay. Yeah. So here I go from, I have an input of 200 millivolts. So I go from minus 400 to 400. Okay. And how much does it take? About one division.
Yeah, 5 microseconds.
Yeah, something like that. Okay, so it's about one division is 5 microseconds. So it takes about, give it or take it, 5 microseconds. If I have a larger voltage, it takes more time. Why? Well, because the slope, if you watch, is the same, right? The slope is the same, but if it has to reach a larger voltage, then it takes more time. So maybe we can even try to trigger like this, okay? And take 2 snapshots, okay? Like here, 1, and we can give persistence, like display, where is it? Display here, and we can give infinite persistence.
Okay.
Then we change to 200 millivolts, and we make another. Okay. So now you see that this is the input and the output with
200.
With 200, and previously it was 600. You see that the slope is basically the same. Okay. So it takes less time because the rate of change of voltage is the same, but because it has to reach a lower value, it takes less time, okay? So maybe you can see it better if I give some offset, but doesn't matter.
No, it's clear.
Is it clear?
Yeah,
okay.
The slope is the same.
Slope is the same, which means that
it's a constant that defines how fast it changes.
Exactly. So if you have to reach, we can even make it even more evident. Let's say that, because here I have like...
Ooh, okay, 1 volt.
1 volt, okay. Okay, so now you see how long we can clear.
Yeah, almost 20 microseconds.
Okay. So, and if I go down like step, okay, maybe that's not a good idea because you can see the transit. If we go down to, again, 200 milli, boom, okay. So here it takes less than 5 micro, and then it takes 4 divisions, 20 micro. This is the reason why, if you have the same signal, let's say that we have 200 micro, but then let's change the gain, okay? So in feedback we don't have 1 kilo ohm anymore, but we can change like with this decade. So this is, let's start again from 1 micro, okay? We have this decade, and we can click stop the persistence, and clear this display. And again, we start with 1 kilo ohm in feedback. Okay. This is a decade that we can use to change the resistance. So if I have 2 kilo ohms, then the gain becomes 3, 4, 5, and so on. Okay. So the input is always the same, but I change the resistance in the feedback, and therefore I have a bigger gain.
You're changing the numerator in the equation.
Yes. So you see that the larger is the gain,
The greater the response
and
time.
at some point it's too big. Okay. So let's say that we go back to 1. Okay. This is now the frequency is about
10K.
10K. Okay. Let's go back to 1K because then I want to show something. Okay. So this is the resistance, the output signal with one gain of 1, so gain of 2, gain of 3, gain of 4, and now it looks still fine. You see something in the transient. Okay, so I change the gain. It seems fine.
Mm-hmm.
But what happens if I have a bigger frequency? Let's say that instead of 1 kilo, okay, maybe I can show it here. I go to 10 kilo, okay, as we were showing before, 10 kilo, okay. Now, if I have a gain of 1, still,
That's apparent.
still you see that something is going on. It's not so nice anymore, but you can still see that it's a square wave, okay. Okay, still there. There is some transit because it takes some time to go up, but let's increase the gain, okay. Okay, 2, 3, 4, 5. Already it doesn't look a square wave anymore. Why? Because it takes some time and it arrives there. Okay, fine. Then there is a flat part. Looks like a square wave. Let's increase the frequency. Let's go to gain of 1.
Mm-hmm.
And let's go to 20 kilohertz. Okay, now let's increase the gain. And let's arrive to a gain of 10, and now you see that it takes about 20, with a gain of 10 it takes about 20 microseconds, and by the time that it arrives almost at the voltage that should be flat,
This is already too late.
it has almost to go down. So let's keep this value here, 20 microvolts, okay? So according to the output, to the slew rate in the output, so it takes about 20 microseconds to reach this voltage. And let's change the frequency, okay? So if we have a very low frequency, okay, you have 20 micro, we have now 1 kilohertz. With 1 kilohertz, yes, you have a transient there of
Nothing.
20 micro. It's there, it's not nothing. Okay.
Okay, so at such a low frequency, it could
Such
be
a low frequency you can kind of neglect,
negligible.
okay?
Yes.
Because the one division is here 500 micro, so 500 micro. Here, if you watch close enough, yes, you have this transient of 10 micro, but okay, you can kind of neglect.
Yes.
You can still see that the signal is a square wave, okay? But fine, let's increase the frequency. Okay, so you can neglect 20 micro first, but again, let's arrive to 10 kilohertz. Now, 10 kilohertz means that now a division here is 20 micro. Okay, 20 micro, another 20, and yeah, another like 50. So this is 50. The alpha period is 50
Yes.
micro, and here is not something that you can neglect anymore. So it starts seeing a little bit how you're doing. Okay, let's increase it. Let's go to 20 kilohertz. And yes, it arrives to the maximum voltage, but we are really at the limit. If you increase 25, 28, 30 kilohertz, then you don't, it starts going down because it doesn't have the time to reach even. the top value. So now we have, how much is the voltage? 200 millivolts. We have a gain of 10, so it should arrive to 2 volts, and that's correct because here we have 2 divisions, so 1 volt per division should arrive to 2 volts. But it doesn't have the time to reach 2 volts because it needs 20 micro. And by the time that we arrive there, you see basically here, it starts making the transient, but once we arrive almost at 2 volts, boom, it gives the order to change, and then it starts going down and change. But then it gives the order to go up and keeps like that. So let's increase even the frequency.
And we'll see the output voltage decrease.
Exactly. So now as we increase the frequency, now we are about 50 kilohertz. Now it doesn't even reach 2 volts, it arrives at 1 point something volts. Okay. Why? Because the output voltage has this limit, it cannot change with infinite speed. It has some finite speed of change in the output, and therefore if you change the input too fast, it's not able to follow the input and change with speed enough, with enough speed the output. Okay.
Mm-hmm.
So that's the reason why if you have a large gain and a large frequency, then the operation amplifier is not able to amplify properly and to behave properly for that high gain and high frequency.
Mm-hmm.
And that means that the maximum frequency that you can admit in the input depends on the gain. So now if I decrease the gain, I go back to a gain of 2.
Oh, it's still pushing it though.
It's still there is some bad thing happening. It's not, but you see that the signal is closer to the input. Still, we have some transient because it's there. It needs some time to reach the value. Okay, but now we have to reach. Now we have the input. How much is it? 200. So the gain now is 2. So we need 400 millivolts. So it needs less time, and it does arrive there. Fine, it's not perfect, but you can see that you have a waveform, a square waveform.
Mm-hmm.
But if you increase the gain, then it's really bad. Okay, so this is the maximum you can get. And okay. So here we have this gain of 2, and this is to show, and maybe you can see better if we go to a frequency where the things were not so dramatic. Okay, so let's say 20 or 25 kilohertz. Let's make 25 kilohertz. Okay, 25 kilohertz. Now it has the time to arrive at the steady state with a gain of 2. But if I increase the gain,
yes,
yeah, you see that again we have the same problem. Okay. I think this is the best way to show that the gain, how the output is limited in its bandwidth by the limited transient that you have in the
slew rate.
In the slew rate, in the output,
Yes.
because of the limitation of the operation amplifier. So let's now go to sine wave. Okay, let's say that we have a sine wave and we have a nice gain of 2, and we have a nice frequency of maybe 1 kilohertz, and everything is fine. Okay, and then increase the frequency. Okay, 1 kilo, and I go. Maybe we can even use the measurements to see something nice. So we can measure the RMS value. So let's clear all the measurements, and we can use the at measurement in the input. It's 141, and at measurement 282. Okay. So it's twice, fine. And even if we want some better measurement, we can measure some averaging. Okay, fine. So the output is 282, is twice the input.
Mm-hmm.
we are happy about that. Increase 10 kilohertz.
Still the same.
Still 22, 20 kilo, 30 kilohertz, 50 kilo. It's kind of increasing a little bit. There is some ripple. But you see something is already going on. Because it's fast, so it takes some time to follow. So it's not automatic. When you change the voltage, it takes some time to follow, but it's fast. So it has, the output has some problem to keep the pace, to keep up. And then eventually you have the same problem. It's too fast, the input, and the output eventually decreases and goes down. Okay. So at 300 kilohertz, we are already in this kind of situation. So what you typically do is to plot the output, so the gain, in this case was 2, the gain, and in the frequency at some point it goes down. So if this is the gain at the beginning is 2, if the frequency is low, it was 2 because it was twice the input, 282 millivolts, so it means that it was twice the input, but at some point the frequency, if the frequency is too large, then drops down. So we identify the cutoff frequency where the gain goes down by a factor of 0.07. Okay, so if we take 282 times 0.707, which is minus 3 dB, can you just calculate how much it is?
282 times 0.7.
707.
199.374.
199. Okay. So we have to find the frequency where the output will be 199 millivolt, which means that it corresponds to a frequency where we have minus 3 dB, and that's our cutoff frequency. Okay.
What's 0.707?
It's corresponding to minus 3 dB. Okay. It's
minus 3 decibels.
Yes.
Okay.
So here it means that here we are going down. Again, because we want to plot everything logarithmic. Okay. If you remember from last lecture. So it's a convention. Okay. So 0 minus 3 dB, it means that instead of 2.282, we have 199 millivolts. Okay. Okay. So let's try to find. Maybe let's increase here the. So here
you're gonna have to fine tune it.
We say 119.
Yeah.
To
almost.
It's about here. Okay.
So
if we have a gain of 2, the cutoff frequency is 167 kilohertz. Okay. Fine. Now let's try a gain of 5. Okay. Okay. If we have a gain of 5, let's decrease again the frequency. Okay. So 5 times 1.41 should be about 850. Can you please check it? So 141.
5 times 1. Sorry, pardon me. 5 times
141. Okay.
705.
705. And I'm a total idiot because the gain is not 5. We have 5 kilo in the feedback and 1 in the input. So the gain is 6. Okay, so
because plus 1.
Exactly. So this is 4.
Now it's 5.
Now it's 710. Okay, so
almost.
Now we have again to find the value of frequency where the output will be 3 decibels less. So it's 710 times 0.707. Can you please calculate? 710 millivolts times 0.707.
501.
Okay, 502. 502. So let's try to see where I increase the frequency again.
And almost.
already something going down. Now we have 30 kilo and already see that
Cutoff frequency is now greater because the gain is less.
no, the gain is larger.
The gain is more.
So the cutoff frequency should arrive first because now we have how much was the voltage that we have to create?
502.
Okay, maybe I can start. Okay, maybe a bit less.
Well,
Okay, EuroTeQ it. So if the gain is 5, now the cutoff frequency is 68. Okay. So now we have a larger gain. It means that the voltage should arrive to a larger value, and therefore it takes more time. So only signals which are slower can be accepted, because only for slower signal the operation amplifier is able to keep up. Okay. So instead of 167 kilohertz, now I can accept only up to 68 kilohertz. Let's try a gain of 10, which means that this resistor should be 9, so 9 kilohertz, and again, let's go down. So now we see pretty much well that it's 10 times the input. Therefore, now it's 141 times 0.07, and guess what? How much you get?
0.1.
Dun, 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 dun. Does it remind anything? Square root of 2? Does it ring a bell?
No.
Well, 141 is the square root of 2, right?
Yes.
And 0.707 is 1 over the square root of 2. Correct? So then, if you take the ratio, is square root of 2 divided by square root of 2 is 1. Okay. Okay. So now let's increase again the frequency. Now we have 8 kilohertz, and already at 14 kilohertz you see that it's going down, and we get one at 1 volt.
There you go.
A little bit something more. Here we go. So the cutoff frequency is 32.8. Okay. Let's be abundant and let's go for 20. Okay. It means that a very low frequency. Now you see, it's already deformed, and I'm only at 16 kilohertz. Okay. So let's go very low. So here we go. So now it's twice, so it's 20 times, so it's about 281. Okay, now again we search
for 1.9.
It's 2 volts. If the gain is bigger, it's twice, it's going to be 2 volts. Okay, and we go down at 2 volts, which is 2 volts here. So if the gain is 20, the cutoff frequency will be 15.4, and let's make the last number large. Let's say 50.
And it looks like the cutoff frequency is dropping exponentially.
Yeah. Then when you plot it in the graph, you will see how it looks like. Okay. Let's take the numbers and then let's plot it on the computer and let's see how it looks like. Okay. So let's go to 50. So 49 kilo
plus 1.
Plus 1. So now you see it's really spoiled. Like even. Okay. Maybe 1 kilohertz. You have 7 volts, 7.1, which is roughly 50 times, because 10 times will be 14 volts, so 50 times it's 7 volts. It's still within the range of our operation amplifier. So if I try to give too large input that overcomes the input, then it wouldn't be able to do it. We can even try.
To make 1 kilohertz too much.
No, in this case it's not a matter of frequency. Now I have, for instance, 100 kilo ohms in the feedback, so the gain is 101, but it's not the voltage that it should create is too large, so it's not able. Exactly, it's not able to produce such a large voltage. So at some point when it arrives here, it's not able to say, I'm sorry, this is the maximum voltage I can produce.
It's clipped.
So I will go back to a gain of 50. Gain of 50 is still fine. In order to work properly, it should create 7 volts.
Okay.
It's Anki-Dory, it works, no problem. But now at 1 kilohertz it's working.
Mm.
Now it should be 5 volts.
Yes.
Okay. So let's.
I'm gonna guess
3
kilo.
3 kilos.
Oh no.
Oh, see, 3 kilos is already going down.
Almost.
6, 5
Okay.
kilohertz.
5.5. Okay, 5.8.
Oh,
6.
Okay. Something, yeah. Let's say it's not very precise, but okay.
Yeah, just ballparks.
Yes. It's about. Boom. Here we go. So for gain 50, the cutoff frequency is about 6.04
Okay.
kilohertz. Okay. Now, you can see something interesting in these numbers. Look, here we have gain of 5 and gain of 50. Okay. So we multiply the gain by a factor of 10, and the frequency
Drops by a factor.
dropped by a factor of 10. So if you multiply the gain and the bandwidth, you get basically a constant value. It's clear with 5 and 50 because you have 5, 50, so the factor of 10 and the frequency factor of 10. But even like here, you have 5 and 10, so the gain becomes twice as big, and the product becomes half, roughly. Now, it's not very precise, so it's not 33 kilo, but probably we should have measured more precisely. But you see that with much volts. And the same here, 10, 20, so the gain becomes 10 times bigger, and the cutoff frequency, the bandwidth, so it means the bandwidth there of the signals which are acceptable, becomes twice, half. Okay?
Mm-hmm.
So that's to indicate that if you plot this in a graph, in a logarithmic,
you should see a straight line.
Exactly.
And
So-
with a negative slope
Exactly.
corresponding to a positive gain.
So here, if you have a gain of 5, the cutoff frequency will be following this line, okay? And again, if you have a gain of 5 or 10, something like that. What you have in the datasheet, in fact, is the value for gain equal to 1. So if you have a gain equal to 1, they tell you that the frequency here is the frequency where the gain is equal to 1. Okay? Then what you do is say, okay, I want to have a gain of 2. You take the value of the bandwidth where the gain is 1, and you cut it by 2, because the product should be the same. We saw it here.
Okay, so it would be F1 divided by 2.
By the gain of, do you want a gain of 10? We saw it here. You multiply the 10 by gain, you multiply the gain by 10, and the bandwidth is reduced 10 times. So you get the value where the gain of the value of the bandwidth where the gain is 1. You want a gain of 10. Boom. You divide it by 10, and you know that the maximum frequency will be somewhere here, divided by 10.
All
okay?
right.
Okay. So this is to show in real life, first of all, why this phenomenon happens. Okay, the reason why at some point for larger frequency the output drops. Okay, so here you have your very nice output. It's everything fine. But then you increase the frequency and it drops down. It's not magic. It's given by the fact that there is a limitation in the speed.
A physical limit in the op amp.
Exactly. And you can see it better if you watch it in a square wave. because there you see that you have the transient where the op-amp tries to follow the input by following that procedure that I explained last week, that it checks the inputs and then with the feedback say, okay, a little bit more, a little bit more, a little more, until you get to the point where you have this, again, input difference of voltage between the input equal to 0, okay? And, but the speed of this process is limited by the rate of change of the speed of change in the output, which depends simply on the limitation of the operational amplifier, and it's always the same. So if I decrease the gain here, the speed is always the same. Okay. And again, if I have this sine wave
period now. Oh, okay, frequency.
If I have the again the frequency, if you see now.
Why was it distorted there earlier? Like that? Like no, go back.
Okay.
You zoom, drop the frequency. No, drop the frequency.
Okay.
There.
What do you mean distorted?
Why are there steps?
This is sampling. This is
okay.
the scope as some discrete steps. So if you.
So that's determined by the LSB or something else?
Yeah, this is. I don't know. I'm not sure if this is a limit of the LSB of the analog to digital converter, or simply the screen, because there are some finite bits on the screen. So
yes. Probably that's the limit.
I don't know. Maybe we should check in the
that's
specification.
Okay.
But as a matter of fact, the scopes are not intended to have very large LSB, because like this one has 2 gigasamples per second, which means that it must be fast, because you want to see the signal fast. And if they are fast, you have to accept that the resolution in LSB will be poor. You cannot have both fast and very high resolution analog to digital converter. Typically, you have some flash analog to digital converter which are fast, as the name suggests, but it's not very. The LSB is not very large.
Then there was like the integrator.
Then you have other, but for scopes you have flash.
Yes. Yeah. Sorry, we digress.
So, so here what is interesting here is to see that they are in phase. For low frequency, they are in phase. Okay. Once you increase the frequency,
yeah, they'll get out of phase and the amplitude will drop.
Why is getting out of phase?
Because it can't keep up with.
Exactly. So it tries to follow, but it's always late because once the signal changes in the input too fast, you see it very well here. It cannot keep up, which means that you see for low frequency you have this trans. So you see that here you have this
delay.
The delay, okay, and we saw why it happens. And when you go to sine wave, you can see how the delay increases and simultaneously goes down. Decreases because it cannot keep up. Maybe we can show something interesting, because as I said during the previous lecture, this voltage VD, the voltage difference between the two inputs, typically they say people, it's 0. Not always. It's 0 once you arrive here at steady state, but in the middle, when it's moving from one state to the other, it's not 0. Actually, when the operational amplifier feels that the input is not 0, it will change the output in order to have this voltage equal to 0. And that's how the operational amplifier works. Okay? If the operational amplifier is fast enough, it will change so fast, it will be so fast in changing the output that you don't even realize that the input has some difference. Okay? But like in this case, we see that the input changes very fast, and it takes some time for the output to change. So we should see here some voltage difference between the inputs. How do we measure it? Currently, we have a probe from the scope here. Okay, so let's say that we have our, I don't know how to draw a scope, a probe of the scope.
Just make it blue.
Okay, something like this. Okay, so the first channel is connected here to the input, okay? And we have a second probe here. The channel 2 measures the output, okay? What's the problem? Now, I would like to measure the voltage here, but I cannot stick a probe between these 2 points, okay? I cannot measure the voltage between these 2 points. Why? Because this probe of the scope is connected to the ground, okay? So, which is the ground tier of the scope, which is the same ground here. So, if I take for instance, this probe, and I connect it between these 2 points, then I will connect this to ground.
And you're shorting out.
Yeah, so which is not a really good idea, okay? We don't want to mix up the grounds. The ground should be common. The ground should be always at the same point. So what I can do is to take the second probe and measure this voltage, okay? So I put the second probe here, and then I measure the voltage at the positive input, which is something that we are already measuring.
Yeah, we know it.
Okay. Then the voltage as the negative input, and then mathematically I take the difference in the scope. Okay. So what I do is to take the second probe and connect it to the negative input, which is this point here. Okay. And then I calculate with the
difference,
the mathematics here. I take the difference between the 2 channels, okay? And here you see what happens when you change the voltage. It's 0. The difference now the purple is now the difference between the positive and the negative inputs. Okay, maybe I can even remove this, which just makes things complicated. So the voltage between the negative and positive input typically it's 0. Okay. Here we have the yellow as 0 in the middle. Here the purple as the 0 here. Okay. So this is the level 0. So it's true that it's always almost 0. Okay. So if you
what the hell? Oh yeah, it's oscillating.
So it's almost always 0. But when you have the change, then boom, you have this transient where the difference, now the purple now is VD, okay? You see that VD, when the input changes,
it oscillates.
I wouldn't say oscillate.
Well, okay, there's a transient.
There's a transient, so it's not 0 anymore. Then the output will change until it gets back to 0, okay? And if I increase the frequency too much, then, and I arrive to the points where it is not able to keep up, then, okay.
Well, the transient also grows.
Then you see it's never going to be 0, okay. I can even try to see sine wave, okay. If the sine wave is slow enough, then it's always going to be 0, okay? Now the input and the output will be in phase. So if I watch at the output, now this is the output, and I remove the math. So input and output are in phase. It's fine, okay? It means that the output is changing fast enough to keep the input always so close to 0 that in fact you don't see any difference. And when I increase the frequency, then they will start getting out of phase, okay? Because the input is changing so fast that the output is not able to keep up, okay? And in fact, if we watch at the VD, so now I measure again as I explained before the VD. VD is almost 0 for low frequency, but as soon as it starts getting out of phase,
the difference gets greater.
Then VD starts appearing. In this case, when you are out now, because the frequency is 125 kilohertz, and we are getting close to the point where there is the cutoff frequency. Now you see that VD is almost never 0. Okay, so this idea that VD is equal to 0 is not really true. Okay, it's true only if you are
steady state.
Steady state, or if the frequency is much lower than the cutoff frequency.